Mhm. Hi everyone. Hi. So let's continue with SQL. I make quick let me remind you for what we've seen. Besides different integrity constraints like primary keys, unique keys, and referential integrity, cascading, and so on. Last time we've seen inserts, updates, and deletes. So simple form or not so simple literal form, and result of using select results to insert into another table. And come to queries. And querying main form is select from table, select list of expressions, and we can use not only just field number, field name, column name, but we may use functions, we may any expressions. So and including constants. So I may say select, and let's say number 1. So every record in the table will contain just number 1 in this column. So that's allowed too. So where for filtering conditions on single record. So every check in a var section, in a var clause, is applied to only single record, current record. Current as thinking about looping through the table. Ordering is ordering. Duplicate may be eliminated, and in many cases we do want to remove duplicates. So keyword distinct. In many systems, keyword unique is maybe used to remove duplicates, but distinct is most standard. Joins, old syntax using comma, and then we'll go to modern syntax with join, with keyword join, and on inner join, outer join, and so on. And we come somewhere here. So for to refer to tables, so I need to say I need to refer to field to column stud ID in table student and in table attends. So I need to qualify it and use for qualification table name. Instead of table name, I may supply an ls and then use ls as here, a there, and so on. In some systems, I may mix. So I may, even if a student has an ls of s, I still can use student.name and s.std. In some systems, that's not possible. Oracle don't allow use name of base table if ls is defined. So if ls is defined, we must use ls name. Field renaming of attributes is also possible in this form, and that might not be just an attribute, but also an expression or even a subquery. As for set operation, we use keywords of union, intersect, and minus, and then we need to build a table, logical table. Result of selection is a table, is a relation, and then let's say union it with another table of the same structure, or find an intersection, or find all the records from first table with the exception of second, that's minus. Anyway, both tables should have the same structure, but in terms of number of columns and their types, data types, but it's not mandatory to have the same column names. Column data types should be compatible and only in one direction. So essentially, result of such an operation of union, of intersect, will have the same schema as first select. If I have select name, comma, something, comma, something, comma, something, then exactly this structure with this name, with these names, is a schema of resulting table. And in second and the next queries, I need to supply something that can be converted into appropriate types and so on. So names from second select don't count and don't use, and SQL engine don't use anything from second and third and next selects besides just values, and try to if values may be assigned to cells of results, then that's okay. Grouping and aggregation is next big thing. After join, we may group the total. We may group the whole table and calculate something. So select average, calculate average for a column, or calculate sum for a column, or maximum or minimum, and so on. And we may group it first, just divide a whole table into groups, and each group has something in common, and that in this case person number is the same for the whole group. For each group, all the records in each group have the same person number. Essentially, we divide lectures between professors. So group of lectures for that professor, for this professor, and so on. And result contains just single row, single record in a table of result for each group. Each group, all the information of each group is compressed in a single row. So that row may contain columns from group by clause, so person may be output, as group as a whole has the same value, just single value for person for the whole group, and everything else need to be put onto aggregation functions. So make just single value for the whole group. Sum is single value for the group. Minimum is a single value, and so on. And group may be filtered using having. After group by, I may add having and use aggregation function and compare the results with something. Only groups, only such groups that have correct, not correct, just of aggregation function value in a condition lead to true, such groups will be added to result. So that's grouping. And then subqueries. Subqueries are very useful. In most cases, we may rewrite subqueries in a form of joins. In some complex subqueries, it's hard to do so, but nevertheless, it may be possible. So I want to find all the professors who has no lectures. So I need to loop through, I need to go through professor table, look at each next record, get a record, and then put here value for professor number, and then execute internal selects, that subquery, and that subquery correlates with the current record, as it contains value from the current record. Such subquery called correlated subqueries, and correlated subqueries need to be executed for each record individually, for each record of outer table individually. So I look at first professor, select all the lectures for exactly this professor, and if list is empty, then so not exists, return true, then that's exactly the professor I search for. So I search for professors without lectures. So, okay. And if a list of lectures contain at least single lectures and not exists, return false. So we skip this professor and don't add his name or her name to an output. That's correlated subquery. In some cases, we may use subqueries that's non-correlated or uncorrelated. In this case, I have a query that has no references to professor table. So select something from lecture, that list, that subquery may be executed just once. If correlated subqueries need to be executed multiple times, if professor has 50 records, then I need to execute this 50 times. 50 different queries with different argument, different parameter values, different conditions. And here I may execute subquery just once, have a list of person numbers who deliver lectures, and then just check each professor that professor's number is in this list or not in this list. I search for professors whose numbers not in this list of professors who deliver lectures. Probably second, this formulation result are the same. So both queries are results in the same list of professors in the same table. But probably second option is faster, as I need just execute this once. So go through lecture table just once, and then go through professor table. So one scan of lecture tables and one scan of professor table. In case of naive execution of correlated subquery, I scan professor table once, and for each record, I need to scan lecture table. I need to scan lectures table as many times as there are professors. So if I have 50 professors, I need to scan lecture tables 50 times. And here, just single scan. That's in naive, if execution is naive or nested loops. But in many cases, optimizers may find a better way to execute query. And even in case of correlated subquery, it may be faster. It may convert it into a join and then apply multiple join optimization methods. But the result will be the same. And I would better to not to hope to put my hope on optimizer, but I'd better to perform my part of work, like here, and create simpler query. So chances would be better to optimize this query than that. Special keyword all, besides in, not in checks for presence of a current records value in a list. Exists check for existence, non-emptiness of a table of result of subquery. And all checks condition with every result. So exists just checks that there are some results, at least single record. In search for single value that's equal to current value. And all check condition for all each and every value. So I need to check that my semester of my student is greater than or equal than each semester for each student from a table. And If true, then student go to result. Essentially, that query is searching for students from last semester. So students who have no other students with the maximum semester value, and it may be rewritten as semester is greater or equal or just equal. Select max of semester without all. As select semester, return a list. As select max of semester, return just single. It returns a table of single column and single record and single row, just essentially a single value. So select max of semester returns, let's say, 12, and then I search for student whose semester equal to that value of 12, and that's all. Subqueries may be put not only in var, but also to select condition, to select list, person number. For each professor, I output professor number, name of the professor, and result of calculation of execution of this subquery. And that subquery go to lecture table, search for p person error is correlated value, substitute it here, and search for all the lectures for delivered by this professor. And I can't output all the lectures here. So only single record for professor. And so atomic value should go here. So I need to maybe group something or do something else. And here, just group all the points for all the lectures. So select sum is just a number. Person, name, identifier, name, and a number. That's good. Some systems like Oracle has additional special, or not additional, special non-standard functions. In Oracle, we have list ag from list aggregation function. If I put it here and say list ag of, so use list ag in this select, then it select may return multiple records, and they will be aggregated in just single string with delimiters. But that's non-standard. Other place to put subquery is from professor, and some select, and I have no restrictions. If here I have restrictions on what should be returned, only single value or some special function. And here there's just another table with an alias, and that's it. So all the lectures grouped by professor number. So there's a table of pairs, professor and sum of points, professor and sum of points. And then we may use it in joining, let's say. And result would be, in both queries here, result would be the same. So queries may be rewritten. And all the rewrites are directed, in most cases, to equivalent join queries. I may find assistants who are older than their respective professors. So I try to search an assistant such that there is a professor who is a boss for this assistant. So professor's number is in a field of boss for this assistant. And professor is younger than assistant. If I can find such a record, I don't output a professor's data, but just output only assistant data. So I need only check existence, check only existence. And here I may rewrite this query in different way. So I search for pairs. I check all the pairs of assistants and professors and check whether this assistant has this professor as a boss and professor is younger than assistant. Essentially the same, exactly the same wording if I try to describe what's happening, but different representation, different queries. And join queries, for joins invented, there are many methods of optimizations are invented. And for exists, main method of execution is just nested loops. I need to loop through scan all the records from outer table and re-execute internal or so inner, not internal, inner query, many multiple times. So that's not too efficient. And if query is written in equivalent join query, for joins, there are different methods of execution: sort, merge, join, hash join, nested tables too, but that's just one of the methods, just single method out of big list. To run relational division operation, SQL doesn't support relational division. And if I want to find all the students and students who didn't attend lectures, so that student with no lectures attended, how to express this? Oh, sorry, not no lectures, but students who attend all the lectures. One way is to express it this way. So I want to find all the students, and for every student, I loop through the students, and for every student, for each student, I try to find a list of lectures that this user, that the student didn't attend. So I want to find such a student. There is such that there is no even single lecture, not exists such a lecture. And lectures of what kind? And that lecture is of 4 points, and attendance record doesn't exist for each this lecture and this student. So if I can find at least single lecture that is not attended by a student, so student didn't attend all the lectures. So that's not what I search for. But if there is no such a lecture that this student didn't attend, that's great. That student has attended all the lectures. So, and different way, completely different way, I just group all attendance records by students and just count them. If student attended, let's say, 10 lectures, and the whole list of lectures contains just 10 lectures. So that's it. So that student attended 10 lectures out of 10. So student attended all the lectures. So I don't need to count so in principle, I need to have a list of lectures, list of attendance record, and pair them, map them, match them. But I don't need to. If I want to find students who attend everything, I need to just know, oh, we have 100 of lectures. Oh, student attended 100 of something. Great. So perfect match. So that's simpler. In case when a student can't attend the same lecture multiple times, but key in the table of attendance doesn't permit it. So each pair of student and lecture may be met just once. So that means that query is correct. If not, if lecture may be attended multiple times, then we need to use to make that attendance records somehow unique. So we need to use distinct and so on. But in this case, that's simpler than writing something like this. If I want to consider only 4 points lectures, I filter them here. I check that attendance. Here, I just look at all the attendance records, but I need to check that student attended all the 4 points lectures, and I don't care for others. So I need to find all the lectures. So attendance records for only lectures with points equal to 4. I need to join it and search for what I want. And here I need to select count from lectures where control points is 4, and that's it. So I restrict here all the attendance records by lectures with CP4 of 4 and restrict to the right. So the same thing, but just more complex restriction. Very controversial topic in the whole SQL is about nulls. And a null or nil in languages and programming languages, not in SQL, but in different programming language. In SQL too is famous. Null values is so famous that some people publish articles, publish posts under idea that's that null is $1 million worth error or $1 billion worth. So idea of introduction of null value leads to hard to find errors in the code. So if I just didn't assign a value to something, and if there would be no possibility to assign a null, then I need to do something and to find why we don't. So that would be that would push us to refine our model. But in presence of nulls, we just declare that this column can be null, this column is nullable, and this is nullable, and then we have just records almost empty, just a key and just few fields out of, let's say, 10, and we don't know. Null may mean different things. Null may mean unknown. So let's say I have a records of about people, each record for single person, and column date of birth. There are no people who have no date of birth. Somehow they was born. So that's just my shortage of knowledge. That's just unknown to me, but it exists. So in the world, date of birth of this people, of this person. So null here means that's unknown. We don't have this data. In other cases, it may mean that's it's not existent. That's not simply unknown. That's not possible to have a value here. So that's completely different null value. It's just a placeholder, not a placeholder, but for some people, maybe some fields may be non-appropriate to set. That's that never will be assigned value if there's different situation. So now nulls are different, but let's look at their usage, as nulls are still used in some places, and some companies try to restrict their usage. Let's look for this query. Student, I'm trying to count records in the table restricted by values. Semester lesser than 13, or semester is greater or equal than 13. And I look at this this condition and say, oh, so it's just all the students. So if we have 50 students, some of them on semesters that's lesser than 13, and some of them are on semesters that's greater or equal. So that's just the whole student list. And then I select count from student, and it turns out that first query return, let's say, 45 students, and second query returns 50. Strange. I think that the first query returned me all the students, and second returned me count of all the students, but numbers are different. So not the problem, but the matter may be that some students have no semester value set. So first query, trying to compare semester of null with this value or that value, returns no. Null is not lesser than something nor greater than something. Null is a null. Null is incomparable with values. It's just not equal to anything. Just another value that's not equal to anything. So counting students. So essentially that's, I want to count all the students who have semester assigned and not count students with null semester. And here I count them all. So queries are not equivalent. How to deal with null values? So rules are almost the same as for nil or null in languages and programming languages. So arithmetics, null is propagated. So arithmetics propagate nulls. If my value is already null, come from, let's say, a column from a record, I get this value, and let's say plus increment it or multiply by something or do something. So if one of the operand in arithmetics operation is null, the result is null. So unknown plus 1 is still unknown. Unknown multiply something is still unknown. And even multiply 0. I may expect that I may multiply anything by 0 and result would be 0. But no, null is stronger. So operand is null, result is null. For if I compare something to something, then a special Boolean value of unknown, true, false, and unknown. And all comparisons that involve a null value evaluate to unknown. Null is null lesser than 30? Unknown. Is null equal to null? That's not. That's unknown. So that's not true and not false. So that's just that's rules of running of working with nulls. New result of comparisons of null with any value, including null, result is unknown. And logics, if I apply not to true, result is false. Not false is true. Not unknown is still unknown. So and classical tables for AND of three value logic for AND and OR. And here we have special way. In arithmetics, multiplication by 0 results in null. And in AND operation, if one of the operands is a false, then be it true or unknown second operator, that can't lead us to anything but false. So false and anything is false. The same is true or anything is true. So true or true is true. True or unknown is still true. So we have true or something, or unknown, but true is already here. And true or false is still true. So false here lead to false. True and true is true, and unknown and true and unknown are all unknowns. And some changes in semantics. In where, without nulls, we say we want to check condition. If condition is false, then we'll throw it out. If condition, and now we try to evaluate, after condition evaluation, we search only for, so we allow the record to next step, to grouping, to output something, only records or the tuples that evaluate to true. So unknown considered equivalent to false. So if semester is null, null lesser than 11, lesser than 13, that's unknown, and unknown or unknown is unknown. So equivalent to false. In group by, in group by special situation, if I have semester of group by semester, and there is a semester of null, group for null value will be created. So I'll have, if there are 13 semesters and some students are not assigned with semester value and all the semesters have students, then select count from student, group by semester, select count of student, group by semester. Result would be a table of how much student on first semester, then on second, on third, and so on 11th, on 12th, on 13th, and on null semester. So that's there is a group for null if a value of null is present. And essentially this not single but main way to deal with nulls explicitly. I can't compare it. If I try to compare something with null, result would be unknown anyway. If I try to compare it this way, result would be unknown. And in var it leads to false, considered false. But what if I want to count exactly semester is null? So semester is null. And if something is null, return true. If value is null. I can't put equality sign here. I can't say semester equal to null. Then result would be 0. No values are equal to null. But is null may return true for null values. And some other syntactic sugar, yeah. I may write something like this: a semester greater than 1 and lesser or equal than 6. I may change it and don't repeat semester name of column and say that semester between this and that, including both ends. Or I may use something like this: semester in and the list. We've seen in this subquery, in and in round bracket, we have select something from something and so on. That's one option, and this option is using just values, just literals. In a list, equivalent to or semester equal to 2 or semester equal to 4 or semester equal to 6. And in execution plans, that depends on a database management system. But in Oracle, we'll see that the method called or expansion. So in is expanded into a list of or. So in some systems, we don't see such an expansion. Very special and good both statement and function. We have case in form of function and in form of syntactical component. So let's look here. Case is if or switch in C. Each time I output something, go to table tests and output each test value besides start ID, and then I check conditions. When grade greater than something, then just value, they're good. When grade greater, so if grade is greater or equal than 5.5, then I output this and stop checking conditions. If not, then I check next condition, and then check next condition, and then check next condition, and else output something else. All my values in then and else should be compatible. So all are strings or all are numbers or so on. And essentially, all the case statement here is just a calculation, is just form of expression. I just calculate or evaluate a value starting with a grade column, and result is a value, a single value for current record that would be put in select list. I may use this case construction not only in select list, but everywhere. In every place where a literal or just atomic value is expected. So I may put this construction to where case when something, then something, so and so on, equal to something. So I just that's just a method of recoding. I have a data, I need to recode it using some logic into completely different values of different type and so on, and then that recorded value may be compared or put under function or anything. So that's just single string value in this case, and it may be operated, may be placed anywhere where string is allowed. So no breaks in contrast with C. So just condition, then value, condition, then value. Different way to, that's called searched case. Different option for case is to put, if I want not to compare with greater than or something, if I want to compare on equality, then I may express this way: case, then column, let's say room, and when one, just literal, then something, when two, then something, when three, then something. So that's a different way to express the same idea. So I may not repeat great equal to this, great equal to that, great equal to that. I put great after case, and when value, then result, when value, then result. This kind of search, this kind of case is more common. I may express not only just compare with a list of values. I may put any condition here. Great is greater than something, then something. Next, when, completely different column, student, substring of student name is, student name has an A being first letter, then something. So I may use completely different conditions, different logic, and even I can build a tree. Case when something, then case when something else, then something else, when. So I may put cases inside other cases. So here, instead of just literal value, I may put another case with its own conditions, and here put another case with other conditions. That's quite hard to read, but in some cases, that's best way to express something. Likes. Like is a built-in operator, built-in statement to compare strings. That's simple operator, simple statement that have just two special symbols. % sign represent any substring, even empty substring, and underscore represents exactly single character. So T% Eophrastus, Theophrastus, if name is Theophrastus, Theophrastus results in true, and TH Eophrastus results in true too. So I may put multiple percents and multiple, like here, %, thick, %. So I try to find a thick or a thickness or myethic or something else. So some symbols here, some symbols there, and maybe empty strings here and there. If % is put only on last position, then that's more efficient percent in first position leads to full scan. So I need to get every record and compare. If I have no first percent here, then I may use indexes to search by prefix and then search records. So percents in front of this matching condition lead to non-efficient full scan of records. Percent being the last symbol allows for more optimal execution. And keywords of join. Joins added only in SQL on SQL standard of 1992. Keywords of join, natural join, cross join, and so on. So cross join is a Cartesian product. Natural join is a natural join. So natural join search for columns with the same name, like in relational algebra, and all the columns with the same name. If I have table, ID here and ID there, and different columns here and there, great. Natural join will find IDs here and there, and then compare them, and output records with corresponding values, with the same value, and only equality. But what if I add, let's say, to first table column named comment, and the same name column to second table? So I added comment or description or something, just why not? I have a table, let's add a description column to this record, and let's add description column here. And most records has no descriptions, they're just empty, but some do. And description here or there, and description here and there. And natural join result, it may result in smaller set, as it would compare not only IDs from here and there, but also descriptions should be the same. As field names, column names are the same, for natural join to be successful on this pair of records, everything is in column named with the same name should be the same. So natural join is fragile. It's easy to change table in a database by just adding new field. What could be broken, but adding new field? But yes, that's possible. Natural join may be broken by this operation. And then join or inner join, and that's preferable to write explicitly keyword inner. So we show that we don't forget that if I write join, one may think, oh, maybe he thinks about full outer join or left join or something. If I put inner, that means that that's exactly what I wanted to put. So inner join, left, right, or full outer join. So left join, left outer join, right outer join, full outer join. So syntax like this: select something from two tables using comma, where condition is exactly equivalent to this syntax: R table, first table, join, next table, keyword on, and condition here. And I may add where conditions and group and having and order bys, everything, subqueries. This is just comma change to join, and conditions put into on clause. And in most systems, if I have multiple conditions, not just single condition of joining, where are A equal to B and column C in R2 greater than 5. And I convert it this way: on join condition where C greater than 5. That's great. But I may switch places and put on C greater than 5 where this condition. It will still work. So if I skip completely on clause, I'll have error. So join R1, join R2, where condition. That's error. You need to have on. But if I write on, okay, let's apply an on clause on 1 equal to 1, some true condition, where a real join condition, it will run. So no errors. Okay, we asked for on condition. Oh, here it is. We have on condition. That's not good way, but almost all SQL systems allow to be fooled by this. So left arrow to join, and let's look. Professor, left arrow to join. Tests, left arrow to join with students. What's the result? If to build this table, tests, left arrow to join with student, I need to find tests. So every test will go to result, even if there is no student record. That's strange, but that's it. And all the professors will be here in the list. If professor take part in student test, then so Russell test by Russell, grade is this for student of that, is name of that. Okay, Socrates tested this person, result is this. Khan tested this person, result is that. Curie, we have a professor Curie, but she didn't test it. No tests for her. So, but left arrow to join outputs all the professors. If some tests may be found, then okay. If not, then just empty values or nulls. Nulls here. Right arrow to join. Professor right arrow to join. Test right arrow to join. So every student should present in the result. If student have some tests, then we have test results and professor and so on. But if not, then student will be here, and Fichte has no tests. So, but record is here and filled with nulls. That's another way. Not another way. That's just how left outer join and right outer join works. And full outer join, I want to see all the professors and all the students. Anyway, if some professors and students made tests, then okay. If not, then professor without data, records for professors and records without data for students will be present. So result of full outer join is like this. Recursion, yes, recursion is a special way to. Yeah, let me check. Yeah. If you want to go by tree or graph, so we have a table of lecture, and table requires are pairs, prerequisites and follow-ups. So if I want to find, let's say, such a lecture, or start with a lecture that has a title, and I want to search in a table of requires that's this lecture of Der Wiener Kreis is a follow-up for some other lecture. I want to find, if I output prerequisite, then I find lecture that's prerequisite for this. So I go up, I go to previous lectures that need to be attended before going to this. And if we look at the path, so to go to Der Wiener Kreis, I need to Wissenschaftstheorie, to ethic, to Grundzüge, and so on. So to take bioethic, I need to take ethic first, and Grundzüge before ethic. So different passes that leads somewhere. So this that's not a recursion. That's just a join of two tables, and that's all. So using this query, I find this Wissenschaft theory. And then what if I want to find make a next step to search what Wissenschaft theory depends on these two lectures. So I have lecture described by title, then first follow-up is here in L2, that requires, and next follow-up is who I want to search prerequisite for prerequisite. So I make two steps, and it takes another join with the same table of requires. So if I want to go for requirements of Wiener Kreis up to some levels, I need to from requires and requires and requires first and second and third and multiple times in lecture, and stack these conditions. L1 follow-up is a prerequisite from L2, L2 follow-up is a prerequisite from L3, and so on and so on. And the last follow-up is equal to number of lecture, and lecture is this. So that allows me to go by this tree to n steps. First step, second step, third step, and so on. But to predefined number of steps to a number of levels. So if I can't tell in advance tree how deep this tree is, then I can't write such a query. So if it could be 10 levels or 20 or 30 or 100 or 1,000, I don't know. So our lecture list grows and grows and grows, and it may grow to just next day it will grow for another layer, for another level. So I can't predict how much pairs of tables and pairs of conditions write to this query. So that's not limited. And I can't, using standard SQL, without common table expressions, without this keyword, I can't express this idea that I want to go to multiple steps down. And Oracle proposed and used and provided us connect by clause to solve this situation. And this situation, and this is written like this. So I need to connect by is for walking by this tree. So it may address only a single table, and table of this kind. It has two fields, and one field is a parent, and another field is a child ID. So prerequisite, let's say, is a parent, and follow-up is a child. And then I say I want to start with something, starting with some node on this tree, and then go to connect these pairs using this condition. So I say that prerequisite is a parent, and follow-up should be exactly should have the same value as a parent. So this query starting with some point go up and up and up, searching for parent and grandparent and grandparent, and it stops only when no parents more. So we found our grand ancestor, and then it stops. It may perform 10 steps, 1 step, no steps, or 100 steps, or 1,000 steps, and so on. So if this switch places, then we go down by the tree, starting with a node, and we step down and down and down and down, searching for descendants. So in SQL 99, in SQL standard of 1999, additional, so standard doesn't contain this connect by clause. That's only, I'm sorry. connect by is not included in an SQL standard, but they created more common way to express recursion. So connect by is for only tables like this, just 2 columns, and we say that we travel going to just checking equivalence if first column here is equivalent to last column there, so that's a child number, and here is a parent number. So that first record is a parent for that record. So if we try to move in this direction, then we move deeper. If we move in that direction, then we move to the top of the whole tree. And recursion that's in standard called a common table expression. Start with keyword. It set a name for this virtual table. That's common table expression. That's expression to define a common table. And that common table called translecture here, that's a virtual table. And we say, we want to describe, to define new table. We have table, base table, lecture, and some others requires and so on. Let's describe new table, just describe. Let's define it. We'll not materialize it, maybe. So how it can be defined? We go to table requires and extract all the pairs, prerequisite follow-up, prerequisite follow-up, prerequisite follow-up. So we'll have just table of pairs, the whole table of requires, and requires contains only immediate neighbors, immediate child or immediate lectures that are prerequisites and follow-ups. But we want to build a transitive closure. We want to find all the pairs that are prerequisites but not immediate. This lecture is a prerequisite to this lecture, then that lecture, then that lecture, and then that. So I want to have a pair of the first and the last lecture in one record. So I understand. So I see all the lectures that I need to take before going to this. So all the prerequisites follow-up go to result, and that may be executed only once, so it doesn't depend on anything else. Just select pairs from table requires, and then union all adds add recursive part, and that recursive part will be calculated multiple times, evaluated multiple times. First time, translecture at that moment, translecture. So recursion is here. I refer to table I'm defining now. I'm saying that translecture contain these records and something else. Let's add new other records union. Which records to add to here? At this moment, translecture contains a result of that first select. And let's do this. Let's do this join. Let's perform this join. Translecture requires. So if translecture has a next second some follow-up, and that follow-up is a prerequisite for something else. So we make just one step from all the follow-ups and search which lectures are maybe attended after this lecture. So this lecture is a prerequisite for that. So we make one step, just single step. So I have all the pairs, and then I make a transitive connection, starting with T first. If I can find such a requires, and they are connected here, T next is prerequisite from here, that means that R follow-up, so next field, are connected to, but transitively. And I select, putting to select here means that I add this pair, that's transitive pair, to translecture table, to virtual table. So I add everything that follows from translecture, making one step. And then my translecture has not only direct neighbors, but the transitive pairs with that are not direct neighbors, but they have common node between them. and then re-execute that second part. So we're trying to build this table recursively. Execute first selection once, and then execute second, and then once more, and then once more, and then one. And each time, if select returns something that added to translecture contains, and next time we execute it, translecture is bigger, has new records, and we may reach something new, joining it with requires. So each time we re-execute this selection, translecture has more records, more records, more records, more records. And if at some moment that selection finds nothing new, so we come to an edge, to end of. So no requires record can be found such that we may make next step. So if selection return nothing new, so we can stop. So no new records will be added. We need not to re-execute it one more time and second time and next time. It will result in nothing new. So if at some step nothing new is returned, then if table stops changing, translecture stops changing, then we don't need to perform that recursion. So that's essentially tail recursion, and expressed in this way. That's not the only way to express it, but every common table expression needs to have two parts. First part is a starter, where to start from, and second part is probably join, but we are not limited. Second part of the query may take different forms, but it needs to refer to itself. So recursion should be here. And all this process of execution of this code results in a table, in a translecture table filled with data recursively and stop. And then that's a prefix to my query. I say, I'll use this name to describe that recursive table, recursively collected table. With translecture as this query, let's select data from lecture and so on, and then use this translecture somewhere in my query. And here I have not only direct connections between lectures, but all the transitive connections between lectures. And then I can find everything that's prerequisite for a given lecture, just looking to translecture, so saying, please show me everything that's prerequisite or prerequisite for prerequisite or prerequisite for prerequisite for prerequisite for given lecture. And the single query return me everything I want. So recursion is here, and then I use it. That's an idea of common table expressions or keyword with from a standard, from SQL standard for something like 20 years, more than 22 years. We have such a language construction. So that's not most complex. Next time we'll look at so-called window function or analytic queries that are standard too and have special way to build complex reports, and many vendor systems do implement it. So that will be our next time. But now just extension on data manipulation language. So if I want to insert data into a table, I may get it from as a result of select or just literal values. Both ways are possible. If I want to delete, I need to provide a condition. What should be deleted? If condition is not here, then all the records will be deleted. Like if I say select from table, I'll see everything. If I add where then I'll see only, yeah. Yeah, I may check it. I just have too much. I just have too much records and messages in Telegram. From time to time, I try to find something, but you better not just send. I'm trying to find your name and yeah, that's yeah, no, I just have no time. I'm to to check and mark all your homeworks. I'm trying to do this, but so that's not a problem of anyone who have no marks. I'll try to fill it in nearest future. So deletes, updates, and with deletes we have, yeah, sorry, yeah. And updates change something. With deletes we have strange, not strange, but snapshot semantics. If my condition is not just as static as this condition, just semester is greater than something. Okay, so I may, that's evident what's the result. But if I try to delete from a table of requires, where prerequisite in something that's selected from requires, if I try to check condition and immediately delete a record, so it may lead to different results. So result will be different for different order of scanning records. So delete has this semantics. First phase is to mark tuples. So go through all the tuples that would be affected and mark them, and don't delete on this phase. And then next phase, go through all the marked tuples and delete them. So this instead, this query will result. What are you trying to delete? I try to delete all the records where prerequisite is in some follow-up. Result would be here is delete all the records from the table, but I tried to I wanted to remove all the records besides the very first layer of prerequisites. So yes, and probably the last thing for today, we have special relational databases has a special kind of additional objects in database called views. And view is essentially a stored text of a query, like macros. Like so, why do we need it? Or in some cases, we just user go to table, to relation, look at it, change data, and so on. But view introduction allows for logical data independence. What does it mean? I may, let's say, describe or declare a view, and set access rights to user to only this view, not for tables. And then user, from user point of view, that's just another table. But under the hood, it lead to a query. Query will be executed. Result is shown. So if my relation contains, let's say, salary for the whole company, and user is a accountant, but not chief accountant officer, chief financial officer, but just accountant for small group of people. If I if I allow access to the whole salary table, so that user need to access salary table, but I don't want that junior accountant to have access to salary data of general director, CEO, and so on. Let that accountant see only persons from some division, and not upper than some level. Then I create a view and say you may see here, and only records that are in that person need to see. It will see only records, only restricted number of records, restricted number of columns, and maybe something will be hidden and something recalculated, and so on. So, and I may even change my relations and only introduce changes into views, and my relations become independent from users. Users look at views, and view is a query. Query may be changed quite fast. And then I create, instead of single relation, I create 2 relations, 3 relations. I normalize them and do something, create this new structure. If I have no views, all my programs need to be changed. All clients, desktop, maybe desktop clients, mobile clients, and everything that access my table, just single table yesterday, and 3 new tables today. So I need to change code on client side, in front end. But if I have a view, I need to just change that view, and that's all. Contents of that view, and interface will, for all the clients, all the users, will still be the same. That's logical data independence. I may change I may change my relations, change a view accordingly, and no users will see the difference. In some cases, yes, views are for privacy. I create a view, test view. After view is created, test view looks like just any other table. I may select something from test view and so on. In some cases, I can even insert data there. And test view shows me student, lecturer, and professor, and no grades. I can see that just the student successfully somehow tested by this professor for that lecture, but grades are private data. You don't have access to them. And access rights to this view I may assign to some users, and other users may be assigned with access rights to other views that have all the fields too. And other way is to make our query simpler. I may perform multiple joins, do it correctly, check everything, and then store it, this query with multiple joins, under new name. This is just syntactical sugar or just simpler queries, and then I just use this stat.prof table with student name, semester, title, and professor name, just as a shortcut. I just select something from this table using names of professors, and that's much simpler than write the same query multiple times. So that's a way to view creation. Yes. So let's stop for now. Thank you. And then
Thanks for the chat.